Get going. Okay, so we have been going through chapter 5 of Sheaf 3 through examples, and we spent a number of sessions together discussing sheaves, and the ideas behind them. Last time, particularly some applications, and in fact, further in the book, we've seen some additional applications for the reading for this time. Things like the N coloring problem, where we color a graph such that no two vertices are connected with other vertices of the same color. And we've seen how those constraints can be characterized as a sheaf. Now, for this class, I want to hit on, if possible, some material that we covered in the readings for this time, but such as that and coloring problem. But I also wanted to talk about co-sheaves. And I wanted to talk about co-sheaves prior to the reading week, especially because some projects in this course might involve co-sheaves. But also because the way we're thinking about sheaves can be dualized beautifully and powerfully for co-sheaves. And in my mind, co-sheaves are equal partners of equal significance to sheaves. They're equal duals to them, and equal in their utility. So I'd like to talk about co-sheaves. There will be a time where we'll be taking on a chapter that discusses co-sheaves at least a little bit. But they're not really given the attention in the book that I think they fully merit. And so I did want to start talking about them today and start to give some flavor of them, even if the formal treatment needs to be deferred. So let's walk ourselves through, sort of resituate ourselves within. You'll recall here that we're dealing here with sheaves on topological spaces. As we'll see in a later chapter, there's a generalization of this that handles sites represented as categories more generally. And these could represent geometric categories, as they're called, like geometric contexts, like manifolds, other topological spaces, and other constructs. Yeah, this comes in with the idea of Grothendieck topologies. But here we're talking about topological spaces where we have posets of opens, right? So we have some situation in the world that has some set of regions in it that have some connectivity between them. And we can represent that as a category, a poset of pre-order category, where each of these nodes are what? What are each of these nodes in this category? They are, begins with S, ends with TS, has an E in the middle. They're sets. And these morphisms are what? In this category, this pre-order of open sets, what are those? They're inclusions. They basically say this is a subset of this, or this is a subset of that, right? You could think of them as subset relations. But a common term used for them are inclusions. And you'll notice that the structure of this mirrors the structure here, bearing in mind that V3 is another portion down here that is in the lower part of it. And note that, and this is an important point, I maybe haven't been emphasizing quite enough. We're talking about characterizing this with respect to a covering of a region, right? So we have this region U overall, and we're not just dealing with the topology, more generally. We're talking about these components that cover that are coverings for a given region, in this case, region U, is the union of these components, and in this substructure is the opens for that, right? So the topology on X may have many different other components, other regions, but this is for this covering U, and that I've depicted, that's been depicted there, and that's a lot of our interests. Okay, so we're going to be dealing here with presheaves, right? Presheaves from this into set, and the idea here is that any presheaf here is going to function in a way that's familiar to you folks, right? If it's from this op, it's going to, for each of these sets, it's going to assign an F of that, right? So if we have like V1 union U3, and we hit it with F, or in this case, it's called S, we get S of U1 union U3, right? And this is just a presheaf, right? And because it's op, that means that one of these inclusion morphisms going this way, for example, turns into a restriction morphism going down like that, right? Familiar? Now, what is this morphism? It's worth, again, reminding ourselves. Over here, they're inclusion. Morphisms are inclusions. What is this morphism? It's a restriction map. It's a map between sets. And in this case, a map between sets, so we're in set, begins with F. It's a function. It's a function. It's a map between sets, right? Map between sets is a function. In set it is, yeah. I mean, again, there may be other categories like rel where map between sets are relations or something, but in this category, in set, these are functions. This is a restriction function, is I think what Mehdi said, and that's quite right. It's a restriction function, right? It takes these items and it relates it to these, okay? So all of this is presheaf stuff, right? These are characteristics that come from presheaf. And so we have these restriction maps, and we have compositions. So we have this morphism and this one. We get a restriction map that goes back in the opposite direction. You could compose those, right? So you could compose over here, V1 to V1 union V3 to U to get a path from V1 to U and map that over. Or you can map over each of those components, V1 to V1 union V3 turns into this restriction map. V1 union V3 to U turns into this restriction map, and compose them here, and you're going to get the same results, right? So what I'm saying, like any functor, it honors composition, right? It turns composites here into composites here. Are we comfortable with that? And that's a characteristic of any functor. It's a characteristic of presheaf, by example. Yeah, that's a constant. We start to use the particular terms, like these terms, like S of U2 or S of U1 intersect V1 intersect V2 or U1 intersect U2 here. We turn these local sections. They're sort of, they associate some data with this particular point, for example, right? Not with the entire thing. That's what we're getting to with this, but with this particular component. So we have all these little islands of, say, possible values that this can take on. Are we good with that? So this associates a set of possible values for this, possible values for this. A particular section will have one particular value for that set, one particular value for that set, one particular value, but the functor associates possible values here, right? And there may be many local sections of particular values, say, for this that relate to these. But once you consider all these constraints, as it turns out, that will come from a sheaf, from really considering this as a sheaf, then we may have fewer values. But we're talking about presheaves now, so it associates some sets of possible values here, and we're good. Okay. And if we have f of x in particular, or here f of u, we're going to have a sheaf over u, so a presheaf over u. Just a reminder of the characteristics of presheaf. This should be fairly familiar stuff. Are we all comfortable with that? Okay. The key thing is, remember, these are inclusions, these are restrictions. These restrictions go in the opposite way as the inclusions because of the op. We good? Okay. Okay. Now, much of the art of sheafs are putting together, like we think about it with bundles, putting together a view of it from one place and a view of it from another place and knitting them together into a combined view, right? So if we have one view here of a set of possibilities, like these 12 possibilities, another view here with these set of 12 possibilities, we want a view that knits them together of consistent possibilities, recognizing that there are some overlaps. So like this has some overlap with this in form of view one. And we need those two pictures to be consistent to glue them together into something for this, right? And it may be that there are specific local sections with respect to this, or specific local sections here, like many of these 12 combinations that just don't jibe together jointly. It needs a special compatible set where these jibe together, right? We need this restrictions here to give a common picture here that is compatible, where the restriction maps down to something here that's compatible with here, in the sense that the overlapping area gives common results, K3, to knit them together into one picture. This one from J1, this picture from K, and this picture from L2. So you can imagine, like, maybe U1, U2 have these two, U1 and U3 have these two, and then we want a picture for U1 that's consistent with respect to those. So they need the overlapping areas to agree. And I should really be talking about these two. They need the overlap here. Excuse me. These two, the picture for this and the picture for this, are going to need the overlapping area to agree to be put together into their union, right? So in other words, if U1 is these and U2 is these, in order to put them together into U1, U2, they have to agree for their intersection, which is this K's, right? And then we can get a picture here that's consistent. We can't get a picture here that's consistent if these disagree. It would be the idea with a sheaf. Okay, but here we're just dealing with presheaf. So I don't want to. Maybe I was jumping ahead there. Okay, so these are presheaf properties, and I was saying where we're going with this. Okay, so let's talk about sheaves here, and I want to motivate this a little bit because I'm going to be contrasting with co-sheaves. So I'm going to take it from a little bit of an angle. You folks will remember, because we've covered it recently, this idea of a limit. And maybe you want to keep in mind a product and a pullback. But in all these cases, what we're going to have is a limit is going to be associated with this cone. And it's going to be a very special cone, the universal cone, the best cone, right? And it's going to be a cone that has projections down to each of these things within the diagram, each of these objects within the diagram. So we have some diagram. We have a shape that maps into our category, and we have a cone over it. And this cone is the best cone. But like any cone, it has to make these things commute, these triangles commute. So every it's a natural transformation is why it has to make it commute. So for every morphism here, we have to be able to either do it here, which is identity, or and then map over, or we have to be able to map down and map over, and they have to commute, right? This is the idea. That's why all these things have to commute. It's a natural transformation. This is kind of a degenerate natural transformation. Okay, but the point is that any cone has to have things mapping down to each of these points that makes these triangles commute here. But the limit is the best one. It's the one such that any other contender, any other pretender that has those characteristics factors through this. This is the best one, the most minimal, the most quintessential one, the one that has the most essential parsimonious description of these things. We okay with that idea? With the limit? Okay, but here's the thing that I want to emphasize. This is going to be really where the kicker comes in here for understanding sheaves from a limit perspective. You'll recall one limit is product. Remember product? Remember what's the product if I have two sets A comma B on the one hand, and another set X comma Y? What's the product of those in set? All pairs. So you want to list them out?
AX, AY, BX, BY.
AX, AY, BX, BY. We good with that? It's the Cartesian product, right? That's the categorical product in set, is the Cartesian product. It is all combinations. Now, do you remember pullback? Remember the idea of pullback? Remember what the idea of pullback was? It was actually a limit, and it had a very specific diagram. It had a diagram like this. So we have an A here, B here. So this is this thing that's underneath here, right? We have an A mapped to C, a B mapped to C, and the pullback was the cone over those. And you know, there's secretly a map from V to C that's not drawn because it's the same going either way, because these commute. We don't even draw it. But you could think there's if you want to think of it as a cone, V sitting over them, there's a map down to A, to C, and to B, right? And this is the best one. It makes all these paths, I'm all okay. It makes all these triangles commute. It makes this commute, and so much so we don't even draw these things. Okay, now, this was the limit, so it's the best one, it's the most minimal one. But do you remember for set, what was the flavor of this? So again, if what did this give? Let me ask this: how does this compare with the product? If we left out C, if the product, remember, it's just the projection down to B and to A. It's like C is the terminal category. It doesn't add any, or the terminal object doesn't add any information. Or if you want, you can imagine leaving this all out. So you just have a projection to A, projection to B, and you consider the product. And now you consider the pullback with some C that's not terminal. That it's not just a singleton. It has some elements. What was the flavor of the pullback? Do you remember? Okay, it's related to the equalizer, because the equalizer is another limit. But so if these are shirts and these are pants and these are colors, and S maps shirts to their color and B maps pants to their color, what's the pullback going to give you? Yeah, shirts and pairs of shirts, pants. That's what the product would give. Product will give all pairs of shirts and pants, right? All possible pairs of shirts and pants. Will, all exhaustive Cartesian product, right? What does the pullback give? It gives a subset of that, right? It gives a subset of those pairs, right? The ones that are of the same color, right? So it's restricting down the set of possibilities to be those where this commutes. It's restricting it down to where these maps match. Mm-hmm. And that's exactly so you get matching pants and shirts, right? It requires all these paths to commute. It requires these to map down to the same value. And I want you to bring that idea here because that's exactly what's going on. Here we have something that should remind you of the sorry, for a sheaf, we have not just any pre-sheaf mapping from a set of opens op that this pre-or with inclusions and sets, right? Sets and inclusions over to this one here. That's what we were talking about a few minutes ago. We have a limit preserving structure. So this here is a co-limit. So if you take its op, it's a limit. If we map it over, it's a limit. This is the best one. This is the one like here through which all others factorize, right? And that has very much the flavor of a pullback. So this is like a subset of the products of these, just like this is a subset of the products of these, right? Pants, shirts. V is a subset of the product of all pants and all shirts, right? This is a subset of the product of these sets. These are sets. Remember, they're sets, right? These mapping over to sets. So these are all sets. This is a subset of those sets such that all these paths commute, right? All these paths commute. Just like here, we said this is a subset of all pairs here, of set associated with A, set associated with B, that makes this path commute, right? But here we're taking that up to another level, but it's the same idea. It's the same limit idea. This is going to be a restriction of these. It's going to take whatever values your combinations of them, but restrict it down to those that are consistent in some way, in the sense that they give a common overlap, that they have common overlap. All their overlaps agree. It's not going to be any combination of U1, the values over U1 with any combination of values over U2. No. It's going to be those that give a common assignment of values to their intersection. And same thing for U1 and U3 and U2 and U3. This is going to be the combination, the subset of the combinations of the sets of over each of these, the product of the subset of the products of these sets over each of these points, such that all these commute. They all give consistent pictures. They all give consistent values. Are we good with that? Are we good with that idea? So it's like a sub-object of the product of these, or subset in this case. It's a set. I could have just said subset, such that these restriction maps are equal. And that should very much remind you of what's going on here. Very much remind you of what's going on here with a pullback. Because the pullback is a limit. And this is a limit, right? I mean, my goodness, if there's only two of these, and you were to cut out don't worry about all these, if there are only U1 and U2, this would be a pullback square, isn't it? It's a pullback square. It's the limit of that. Okay. So if you have that notion, that's a really good notion. But I want to observe something more right now. I want you to observe something more. Here's the deal. To have this sense of restriction, which is going to be so important when contrasting this with co-sheaves. So I'm going to observe something. So this is a set, this is a set, this is a set, right? I'm going to appeal to the case where we simply have projection down. Sorry, it's not projection. We have a set of values here, and we're finding those values in this one, and we're finding those values. Remember, I told you before, like often this is has a bigger set, and this has a smaller set. Here's the deal. Here's the deal. A value here in f of U1. So if we have a value assigned from this, we pick some value from f of U1. if this is just find, if it in the case, and it's not always it is, there's often restriction maps that are more sophisticated, but in the case where this is simply finding this value here, this value has to exist here, doesn't it? That same value. It has to exist here in this one. So whatever this is, it's for those cases where it's simply finding this value down here within this set, finding the set assigned to this within this set. For those cases, it follows that this is only going to be more restricted set than what's down here, because it has to be in this one and it has to be in this one. If it's not in this one, then it's not going to be able to find it in here, right? So what I'm saying is that often the picture with these colimits is such that each successive level you go up, it gets more restrictive, because you've got to find whatever value is assigned here. You got to find it in this set, or its translation in this set. So whatever this is has to be more restrictive, because you have to find it in multiple of these. You have to find in this the values assigned to this and the value assigned to this. This one you have to find it in that and that. And so you end up getting this more constricted view. Let's look at this for an example. I'm talking in generalities here, but let's look at it for an example here, right? So I'm going to look at it. You remember this example, right? So here we have, let's consider this one here. So for the interval 1, 2, interval 1, 2. Okay. The interval 1, 2, any value that's in it that's present, remember, this is for public health restrictions throughout this interval, throughout the interval, the entirety of the interval 1 to 2, right? Any value that's in here has to have been in place in time 1, and it also has to have been in place in time 2, right? If this value red weren't in place at time 1, we wouldn't be able to find it in this one. If it weren't in place at time 2, we wouldn't be able to find it in this one. So it's, in this case, this is going to be no larger than either of those two, right? Similarly, this value here, at time 0 to 2, if we consider all public health restrictions in place for the entirety of the time between 0 to 2, they have to have been in place from time 0 to 1. Right? And they have to have been in place between 1 to 2. So this needs to be a restricted subset of these that are shared, in this case, in common here. And that's the reason we had. Mehdi, you had a question. Yeah. 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 Yes. That's right.
This relation to this maps, and we see that this is kind of extract information. We can extract information for climate 1 and 2 from the bigger interval, longer interval.
Well, remember that. So I'll come back to this point when it comes to Cauchy's, but here the restriction map is from 1, 2 to 0, 2. And I think maybe what you're asking is, could we view this map? I'm emphasizing that because the inclusion, what am I saying? Forget what I just said. This is inclusion map, right? This is the inclusion. 1, 2 is inside. It is included in interval 0, 2, right? We've closed in both cases. The restriction map goes in the opposite way, right? It goes down like this. And I think maybe what you're saying is that like we can find this value here is kind of like sampling it from this. But do remember like the values here, these are things that present throughout the interval. And this again has to do with the restricted nature of this. That like for things to be present throughout the interval, it has to be present for all of this, and it has to be present for all of this. And that's often very much the flavor of what you get with sheaves that I'm trying to emphasize here. Like the values here have to, they themselves, or if you have a sort of a translation-based restriction function, they're sort of corresponding values here have to be present in this and be able to be found in this. And so this, it kind of follows that what's here and what's here restricts the nature of what's here. You're not going to be able to have any old values here because you might not be able to find them in this set. You might not be able to find them in this set. And that was very much the flavor of that example, right? Like the sets of values as you went up were smaller and smaller set of possibilities, because at each level we have to be able to find this value at the next level down. We have to be able to find this value at the next level down. There could be more values here, but whatever are here, we have to be able to have at these different places. And the same thing with the restrictions, public health restrictions throughout sets of cities. These are throughout sets of cities, in all of these cities, Saskatoon, Regina, PA. Maybe there was work from home, but for work from home to be present for all of those cities, it has to have been present for any subset of those cities, like Saskatoon, Regina, or Saskatoon, PA. It has to have been present, right? And it has to have been present here. So I'm saying that often sheaves give this very sense of, as you go up, you're limiting the possibilities. At the least, you're limiting because these things have to commute, right? You're limiting, you can't consider all the possibilities here and all the ones here and all the ones here because all these paths have to commute. But also as you're going up, you're often involving sets of values. They have to have their analogs present in multiple of these intersections below to be present here. The set of possibilities you can consider here is getting more constrained. Just like, if you were looking at these satellite maps or these pictures, the set of possibilities of what's going on here is constrained by what's going on here. It's constrained by what's going on here. It's constrained. The further you go up, the more complete and more definitive and more restricted in the sense of specific. It's tied down. It's pinned down. You have, right? Okay. So this is the nature of sheaves that I'm trying to appeal to. And it does very much reflect, just going back to basics, this notion we get with pullbacks as a limit, right? That a pullback is a subset of all combinations of these because it's constrained. It's constrained by the need to match up. And that's very much what's going on with these limits. They're constrained with the need for all of these restrictions to match up here. And so it tends to lead to things here which are pinned down more, which are consistent. They're held to the strictures of consistency with respect to all these different subsets of the region, right? All these different subsets of the top of the open sets. They're pinned down. They're restricted. Now, okay, so those are my comments on sheaves, and now I want to go on and talk about co-sheaves.